So LeetCode 1671, minimum number of removals to make mountain array. So in this problem, you're given an array of integers and you need to return the minimum number of elements that you want to remove from that array so that it becomes a mountain array. And a mountain array is just an array that has a first part where all of the elements are increasing up to a certain peak element. And then starting from that peak element, then you have a downwards slope. So all of the elements are now strictly decreasing. So for example, here we have an input array of 8 elements, and the longest mountain that you can make is long 5 elements. So you need to remove 3 elements. Okay, so the reason for which this is tricky is because they tell you that you're going to have to return the minimum number of elements to remove, and so many people, including me, go straight, like their head goes straight to, okay, I need to simulate the removal of these elements. But instead, what you want to do is you want to find the longest possible mountain that you can make, and that will always give you the minimum number of elements that you need to remove. Obviously, that is quite clear, right? So how does one go about finding the longest possible mountain that you can make given the input array? One good way, and not optimal, not completely optimal, but one good way of doing it is you pretend, like you loop through all of the indices in the array, and you pretend that that index is the peak of your mountain, even if maybe it is not, right? You pretend that it is. And you calculate what would be the length of a mountain with a peak at your current index. So like you start with index 1, because 0 can't be the peak, because you don't have an upward slope. So you need at least one element to your left and one element to your right. So these are the possible peak indices. Sorry, I mean, these are the possible peak indices in this input. And so you start here and you say, okay, if this was the peak, then how long would my mountain be? And here the answer would be like 0 or 1. It would be just yourself. But 1 isn't acceptable because you need at least 3. But anyway, then you go to the next one and you ask the same thing. Then you go to the next one. And again, here, how long would be a mountain if the peak was here? How long would the mountain be if the peak was here? And you see that that is actually the optimal answer. So when the peak is 6, that is when you have the optimal length, and so the minimum number of removals. And so how does one then go about finding this length? Well, you divide it into the increasing part, so the upwards slope, and then you also calculate the downward slope. And to do that, you can use a very common technique, which is the longest increasing subsequence and the longest decreasing subsequence. So after having calculated those two, let's say that you know that your peak index is this one, then just look at the longest increasing subsequence up to that index, and then you look at the longest decreasing subsequence starting from that index. And those two will give you the final length of your mountain. Okay, so let's just implement that real quick. So let's make this smaller. Okay, so first of all, you just take your numbers length for convenience, and then we do the part where we calculate the longest increasing subsequence up to a certain index. And at the beginning, we just fill the array with 1, because at every index, you always have an increasing subsequence of the number itself. So the length is minimum 1. And then you loop through all of the pair of indices in this way. And if you can make an increasing subsequence, so let's say like j is 3 and nums of j is 3 and nums of I is like 5. So you can basically append nums of I to nums of j to make an increasing subsequence. So whatever was the longest increasing subsequence up to j, you can just append to that longest increasing subsequence nums of I, and now you have a new subsequence that is longest increasing subsequence up to j plus 1, because you've appended nums of I to that subsequence, right? So you can update your longest increasing subsequence up to I with the maximum between itself, so just not updating it, and the new one that you've just made, because you can, right? So yeah, you just use a math max for that with the original value and the updated value, right? And you can update this value because nums of j is less than nums of I. So you can just update, you can just append nums of I, which is one number, to whatever the longest increasing up to j was. Okay, and then you just do the same thing, just instead of up to, you do from. So it's basically like the reverse or the mirror, but it's the same algorithm. And then after having calculated this two, it's pretty easy. You just start with your result being plus infinity, which you will later on return. And then you loop through all of the possible peak indices, and you check what would be the length of a mountain which has its peak at this index. Well, the length would be the longest increasing subsequence up to that peak, plus the longest decreasing subsequence from that peak, starting from that peak. And then you need to remove one, because else you're counting the peak twice, but whatever. And then, given the length of the mountain, you can now calculate the amount of elements that you had to remove from the initial array, which is just the initial array length minus the length of the mountain. That is the number of elements that you had to delete. And now, you update your result with the minimum between your current result and your new result. So if you have a better result than your old one, you update it like that. And then at the end, you can just return the result. So that's it. I'll submit the solution to show you that it works. And by calculating the longest increasing subsequence and longest decreasing subsequence like this, you're doing it in O of n squared memory, which makes the whole algorithm O of n squared time complexity, but there's actually a way to make it n log n. But anyways, it gets accepted from LeetCode, so I think this is the intended solution. And the space complexity is O of n, just to store the values of the longest increasing and decreasing subsequences. So that's it for me today. Thank you for watching, and bye.